yesterday that at the oscillating sequences, and we said that oscillating sequences, to deal with oscillating sequences, we had to come up with the concept of subsequences. So we'll see the concept of subsequences today. Now, different parts of an oscillating sequence moves to different directions. So to deal with them, the mathematicians have come up with the concept of subsequences. It is nothing but an infinite part of a sequence where the terms appear in the same order as in the original sequence. Now, so formally the definition is, let F be a map from natural numbers to R. That is a real. That means F is a real sequence of real numbers, and G is a map from natural numbers to natural numbers. Be a strictly increasing map. That is, for every A, the value at n plus 1 of G is strictly greater than Gn, the value at n of G. Then the sequence F composed G is called a subsequence of the original sequence. Okay. Now this is the formal definition. Now this version is using comprehensive notations. What is that? Let Xn be a sequence and be this original sequence, and Nk be a strictly increasing sequence of natural numbers. That is, N1 is strictly smaller than N2, is strictly smaller than N3, and so on. This way. Then this Xnk, where the sequence is varying over k, that is Xn1, that is Xn2, Xn3, Xnk, going on. This is called a subsequence of the original sequence. Now, if you want to match these two versions of the definition, it's just this Nk is your G, this Nk is your G, and Xnk is basically your F composed G. Xn is your F, so Xnk is F composed G. So Xn1, Xn2, so they are appearing in the actual order they appear in the original sequence. So N1 is the smallest. So Xn1 appears, the term Xn1 appears at the very first among all these things. So that is coming us at the first. And then Xn2, Xn3, and so on. So this is a definition of subsequence. But if you just want to care about this is simply, it is nothing but an infinite part of a sequence where the terms appear in the same order as in the original sequence. That's it. Infinite part. So this is a sequence. So the infinite part will be there where the terms are appearing in the same order. It's not that x2 is coming before x1 or something. So x2 should appear before x5 of always. So that if that situation you can arrange, so then it is a subsequence in the same order in the original sequence. So formally we have this definition. Fine. Examples. Consider the sequence xn where xn is equals to minus 1 to the power n. The even subsequence of this sequence is x2, x4, x6, and so on, and they are all 1, 1, 1, 1, goes on like this, is the constant sequence 1. Similarly, the odd subsequence, that is with the odd indexed terms, so x1, x3, x5, and they are all minus 1, minus 1, minus 1, that is the constant sequence minus 1. Next example, consider the sequence xn where xn is equals to 1 to n to the power minus 1 to the power n. The even subsequence of the sequence x2, x4, x6 is 2, 4, 6, that is 2 to the power minus 1 to the power 2, that is 1, so that is 2. 4 to the power minus 1 to the power 4, that is 1, so that is 4, and so on. So this is then is the sequence of all even positive integers diverging to plus infinity. This we know. On the other hand, the odd subsequence x1, x3, x5, this is simply 1, 1, 1/3, 1/5, and goes on. This is the sequence of the reciprocals of the odd positive integers converging to 0. These are examples. Now, third example, since Q, set of all rational numbers, is countably infinite, we can consider, this is a very important example, listen carefully. Since Q is a countably infinite set, we can consider the set of all rational numbers as a sequence Rn. Okay, so that is a countably infinite set. So we can actually arrange the rational numbers in a sequence, in an array. So then for every real number x, this sequence can produce a subsequence converging to x, because we know that the set of all rational numbers is dense in the set of all real numbers. So for every real number x, this sequence can produce a subsequence converging to S. Anybody, if anybody has got any problem with this statement, that for every real number x, this sequence can produce a subsequence converging to x. If anybody have any problem with that, please tell me now. Because Q is, mute your mic. Because Q is dense in R, the set of all limit points of Q is the entire set of R. So, for every real number x, you will find a sequence of rational numbers converging to that real number. This we have found in the by the density property in the last semester only. Okay, in the density property and using the limit point, the definition of limit point. So there is a sequence of rational numbers converging to given a real number, anything arbitrary, there exists a sequence of rational numbers which converges to there. So that sequence of rational numbers is basically a subsequence of the sequence of all rational numbers. So therefore, Rn has infinitely many convergent subsequences. Therefore, Rn has infinitely many convergent subsequences. Extremely important example. In what happens in the examples of subsequences, you do not usually come across with an example of a sequence having infinitely many convergent subsequences, but it is always very essential to know that this kind of sequences do exist. The sequence of rational numbers is one such example. So this sequence of rational numbers is a sort of a built-in example. This we have seen by observing their properties, and this is one such example. The next example is something what I made up. Now, something I may tell you from my college life, that when we were taught sequences over there, we were in first year, and the portion that Q is countably infinite, that thing was not taught to us at that time when sequences were being taught. Now, so for the there I came across with a particular theorem which talked about infinitely many subsequential limits, and then I sort of thought about that why do we need to care about infinitely many subsequential limits of a sequence? We do not have any example in front of our hand. So I asked my I do not know whether I asked my teachers or not, but even if we could ask our teachers. Um, so I came up with this example after sort of 1 or 2 years in the third year maybe. So this is a sequence which has infinitely many convergent subsequences. This is constructed in a very nice way. Understand this carefully. Xn is equal to two things. When n equal to n p to the power r for some prime to the power r. So n equal to p to the power r for some prime number p and some positive integer r. Otherwise, so these are the two cases. So when a equal to p to the power r, what happens? This is 1 plus p plus 1 by p square plus 1 by p cube up to 1 by p to the power r. Otherwise, it is 1 by n. So first few terms of the sequence are, so here you see x1 is 1. So x1 is of this form, otherwise form, so it is 1 by 1. x2, so this is this form, p2 to the power 1. 2 is a prime, n equal to 2 to the power 1 form. So this is 1 plus 1 by p. So this is 1 p to the power 1, so 1 by p to the power 1. x3, 3 is prime, so this is also this 3 to the power 1 form, so 1 plus 1 third. x4, 4 is 2 square, a single prime, square of a single prime, so p to the power r again. So this is 1 plus half square over here. 5, prime again, so 1 plus 1 by 5 from here. 6, a composite number, so this is otherwise, so 1 by 6. 7, prime again, so 1 plus 1 by 7. 8, 2 cube, p to the power r, so 1 plus half plus 2 square plus 1 by 2 cube. 9, x9, 3 square, so p to the power r again, so 1 plus 1 third plus 1 by 3 square. 10, x10 is composite, so 1 by n. x11, prime again, 1 plus 1 by 11 from here. x12, composite, so 1 by 12, and so on. So x13 will be 1 plus 1 by 13, x14 will be 1 by 14, x15 will be 1 by 15, x16 will be this way, one more term over here in x8, so this way. Now, understand this thing. The best part is, the beautiful part is, for every prime number p, the subsequence x p to the power r. So that means x2 to the power r, let's say. So x2 square, x2, x4, x8, x16, x32. This subsequence I'm talking about. So x p to the power r. This subsequence converges to p by p minus 1. How? Let me show you what happened. Okay, let me show you one thing. How it is p by p to the power p by 1 minus p. I should have brought this up before only. Come on. Okay, so this is going from this 1 plus half, so for x p to the power r, this is the term x p to the power r is basically 1 plus 1 by p plus 1 by p square plus 1 by p cube up to 1 by p to the power r. So this is an infinite GP series, with common ratio 1 by p. So this goes to first term is 1 a by 1 minus r, 1 minus 1 by p, that is your this one, common ratio. So this is p by p minus 1. Okay, so this is p by p minus 1. That is why I'm saying that the subsequence x p to the power r converges to p by p minus 1. So for every prime p, this is a subsequence converges to p by p minus 1. So we have infinitely many primes, and so we have infinitely many subsequential limits, I mean convergent subsequences or converging to over here. And the subsequence with otherwise indices converges to 0, of course, 1 by n. So this example will be of particular interest later. So this is another example. I mean, made of example, not a trivial example like the sequence of rational numbers, having infinitely many convergent subsequences. Okay. The above example convey that different subsequences of a divergent sequence is not a convergent sequence. That is what is divergent sequences. So of a divergent sequence, converge or diverge to different limits. To associate these limits of different subsequences to the original sequence, we adapt the following definition. So understand this thing. The above examples convey that different subsequences of a divergent sequence converge or diverge to different limits. Converge to something or diverge to infinity, something like that. So to associate, so these limits, so this p minus 1, this p by p minus 1, this is a particular number which is very much associated with this sequence. So that association we need to study now. Okay, to associate these limits of different subsequences to the original sequence, we add to the following definition. The definition is of subsequential limit. Let xn be a sequence of real numbers. A number x, finite or infinite, is called a subsequential limit of xn if a subsequence of xn converges or diverges in case of x equal to plus or minus infinity to x. So that is the definition of subsequential limit. So here we have characterized or associated these subsequential limits, those limits of subsequences with this original sequence. An immediate characterization of a subsequential limit is as follows. Now, let x be a real sequence. A real number is a subsequential limit if and only if every neighborhood of x contains infinitely many terms of xn. If and only if every neighborhood of x contains infinitely many terms of xn. Now, from here, I must tell you that I have, as I was doing in the previous classes, I have gathered a few results with their proper relevance and have skipped their proofs. If you need the proofs of any of these theorems, you may go to the book, or if you still do not understand, you can always ask me. We can do the proofs in the next class. Since this is a recapitulation class, I have skipped the proofs of these theorems. Now, this theorem is an if and only if condition for a subsequential limit. A real number is a subsequential limit if and only if every neighborhood of x contains infinitely many terms of xn. Now understand one thing, that this criteria, this theorem is for finite subsequential limits, because we have seen that infinity can be a subsequential limit as well, but this criteria you cannot throw over here, because the real number x is a subsequential limit, because you cannot consider a neighborhood of the point infinity. So real number x is a subsequential limit if and only if every neighborhood of x contains infinitely many terms of xn. Now, this theorem if you had any problem understanding that why there should be a subsequence of rational numbers converging to any given real number, this theorem guarantees that once again. Because for every choose every real number x, So I can write over here as well that why there is a subsequence converging to a given real number. Subsequence of rational numbers converging to any given real number. The answer is since every we know this thing. We know that closure of Q bar uh, yes. So this is double Q. Yes. Closure of Q is um, R. This we have seen in the sixth in our chapter in the last semester. So that means this implies every real number x um, has has um, let me phrase it in this way that every neighborhood of every real number a has infinitely many rational numbers. That is the definition of this adherent point. That is the definition of this limit points or this adherent points, and this is guaranteed by density property of rational numbers. Density property of rational numbers. So by density property of rational numbers, every neighborhood of every real number has infinitely many rational numbers in them. Over there. So as soon as we have that, we can apply this theorem, and this turns out that every real number x becomes a subsequential limit of xn, and that means there is a subsequence of rational numbers converging to that limit. As simple as that. Okay, so that is why this theorem is important. Immediate characterization, infinite characterization of subsequential limit. Now, after we have identified this important factor of subsequential limits regarding an oscillating sequence, the following categorization seems inevitable. What is that? Limit superior and inferior. Let xn be a sequence of real numbers, and let S be the set of all subsequential limits of xn. Then supremum S is called the limit superior or simply lim sup of xn, and is denoted by lim sup, and this way. Lim sup xn. Why it is coming lim sup xn? It should not be. Oh, sorry. I forgot. This here the notation I'm using is actually lim sup is a bar on top of this, and lim inf is a bar down there. In the updated PDF, you will find that notation. This is a different PDF I'm showing you for the video, and so I forgot to update that thing. So the notation I'm using is actually an overbar for lim sup and an underbar for lim in. So that is the notation I am using in the, and you can see that in the attached PDF as well. So then sup S is called the limit superior, and infimum of S is called the limit inferior. Now the first question is, what happens supremum is infinity, or what happens infimum S is minus infinity? That means S is not bounded. We have a solution for that. If for some sequence xn the set of all subsequential limits S is unbounded above, we define lim sup to be plus infinity. Similarly, if S is unbounded below, we define lim inf is minus infinity. Examples for the sequence minus 1 to the power n. So we will be doing these examples only. Yeah, these 4 examples of subsequences what we saw, we will try to find out the lim sup and limit of these examples only over here. So for the sequence, this one limit superior is 1 because if the set of all subsequential limits is minus 1. Printing mistake. Minus 1 comma 1 for this one set of all subsequential limits. So therefore, limit superior is supremum of S, that is the maximum of S, that is 1, and limit inferior is infimum of S, that is minimum of S, that is minus 1. For the sequence, the next one, n to the power minus 1 to the power n, the set is 0 and infinity. Odd subsequence was converging to 0 and the even subsequence was diverging to plus infinity. So the set is 0 and infinity. Okay, this is 0 and infinity. It's not 0 to infinity, mind it. This is 0 and infinity. Hence, lim sup is infinity and lim in is 0. Fine. Next one, for the sequence of rational numbers, the set S of all limit points is R. Hence, lim sup is plus infinity, whereas lim in is negative infinity. I don't know why, but I hate this notation. I just forgot to change this one in this video format. And whenever these things are coming in front of my eyes, I'm getting irritated. Okay, so now consider the sequence in example 4, that is this one. Okay, so here in the first look, it seems that the set of all subsequential limits is this, right? P by p minus 1, that is for every prime p, we are getting this number as a subsequential limit, and another sequence is converging to 0. The question is that all? Can there be any more subsequential limits? Okay, because I mean we have seen that things can be pretty that's not organic, let me say. That whatever seems so far seems, it may not be that the case. You have found this kind of ambiguity while finding the limit points. If you remember those examples were done in MAPA, where they have found limit points 1 by n plus 1 by n, that set, the limit points of that set. It is not that easy to find that quickly, that what should be the limit points over there. So you need to pay some close attentions to those things. So therefore, there the set of all subsequential limits is this one. This is coming from the first look. But is that all? Can there be any more? Can there be any more subsequential limits? The answer is given in the following theorem. Let Xn be a real sequence. The set of all subsequential limits is a closed set. The set of all subsequential limits of Xn is a closed set. This is extremely important. That means over here, p by p minus 1, this was coming. Now this one, as p tends to infinity, p is a prime, p tends to infinity, then this guy over here tends to 1. That 1 is a limit point of this set S. So this theorem says that the set of all subsequential limits is a closed set. So 1 is a limit point of this set. Now since this set has to be closed, 1 also needs to be included in this set. Otherwise, this set is incomplete as a set of all subsequential limits. This set does not include every subsequential limit. One is a subsequential limit by this theorem. This is a closed set. So one is a limit point of this set that we can see for sure. So one has to be there inside this S. So this above theorem guarantees that S actually in this case is actually this P by P minus 1, P is prime, union 0, union 1 as well. That is, 1 is also a subsequential limit of xn, which is not so easy to see if one is trying to find a subsequence of xn converging to 1. At a first glance, you will not be able to see, won't be able to extract a subsequence which is converging to 1 from this one, because no subsequence over here you can see is converging to 1. So I mean at the first look, so it needs some special tools, special results to extract a subsequence which is converging to 1 for this particular example. So this is the that I mean this is the reason, this theorem is the reason I actually tried to look for an example of this form of this form, that why do we need to bother whether the set of subsequential limits is a closed set. So far what we have seen, if we did not have that example for the example of rational numbers, whatever examples what I had seen earlier was there the set of all subsequential limits is always a finite set. And why do we need to bother when for a finite set it is always closed set? Why do we need to prove a theorem for that one? So then I came up with this example which has infinitely many convergent subsequences, and so that we actually need this theorem to guarantee that one is also there as a subsequential limit. Fine. A corollary to the last theorem is xn is a real sequence, and lim_sup and lim_inf are respectively the greatest and least subsequential limits of xn. Now, what do I mean by this? Lim_sup and lim_inf were primarily defined as supremum of all subsequential limits. Now, supremum of all subsequential limits. So now, so this last theorem guarantees that the lim_sup and lim_inf, they also have to be subsequential. They themselves have to be subsequential limits as well. Just like over here, one, if you forget about this 0, then 1 is the lim_inf. Okay, forget about 0. Just make this otherwise sequence, tend to somewhere else. Let's say 2. Consider this is 2 plus 1 by n. So then this one will be of the lim_inf of this sequence. In that case, we do not have any ready subsequence which we can show that it is converging to 1. But after this theorem, this says that if you do not have that kind of ready thing, but at the same time that needs to be a closed set. So a limit point, 1 is a limit point, so 1 needs to be there inside S. So there has to be a subsequence which is converging to S. So that is why the lim_sup and lim_inf, both of them have to be subsequential limits individually. Understand? So that is the corollary of this theorem. Okay, if they do not belong to the set of all subsequential limits, then they become limit points, and in that case, since the set of all subsequential limits is a closed set, they have to actually belong to the set. There is no other way out. The study of subsequences have emerged to study the oscillatory sequences. But nowhere in the definition, look at what is the definition says. The definition of subsequence never says that this is a definition for oscillatory sequences. This is a definition for every sequence. Let xn be a sequence. Let fn be a sequence. It does not specify that this is an oscillatory sequence. This is an oscillatory sequence. So the definition of sequence, the subsequence, is does not specify that it is only for the this thing, oscillatory sequence. So the theory is for every sequences, of course. As a result, we can also talk about subsequences of a convergent sequences as well. It turns out that the following is a fact. Let xn be a real sequence. Xn is convergent if and only if every subsequence of xn converges to the same limit. So any subsequence of a convergent sequence converges to the same limit. Every subsequence of a convergent sequence. And otherwise, if every subsequence you can every subsequence of a sequence converges to the same limit, then the sequence will be convergent again. So a corollary to this, the above proposition, along with the last corollary, this one, justify the following, that let xn be a real sequence. Xn is convergent if and only if lim sup of xn is equal to lim in of xn. That means lim sup, what does this corollary say? That lim sup is the highest subsequential limit. There is a subsequence converging to lim sup, and there is a subsequence converging to lim in as well. So this is the highest subsequential limit. This is the smallest subsequential limit. And so if we apply the restriction that they both of them are same, then that means all the subsequences are converging to the same limit, because this is the highest, this is the smallest, and these two are merging together over here. So every subsequence must converge to the same limit, and therefore this proposition comes into play and says that it has to be convergent. And also the other way around, if xn is a convergent sequence, then by this proposition every subsequence converges to the same limit. So therefore lim sup and lim in has to be the same number. So yeah, that's it for today.